Hello, thank you for coming to Science Sunday. As you know, we have this on the second Sunday of the month, usually. And this week I'm going to be talking about seeing particles, a journey to the infinitesimal, how we see things that are trillions of times smaller than atoms themselves. Here you see a picture, which I will explain later, of tracks of charged particles in liquid hydrogen. And they make beautiful curled tracks. It's like art and science together. The next slide, I'll talk about what does it actually mean to see things. Bob and Tilly here said, how can you actually say you see things that are much smaller than you can see with the eye? Well, actually, I looked at the Merriam-Webster dictionary. What does it mean to see? And there are many definitions about seeing. To be perceived by the eye, to perceive objects as if by sight, or also to form a mental picture or visualize something. So here on the bottom you see a diagram with the eye in the middle, and light comes into your eye from outside. It hits the retina, it sends electrical and chemical signals to the brain where you visualize what is outside your eye. So we're just extending this. Light comes from the galaxies, for example, from the Hubble Space Telescope or the James Webb Space Telescope. This is a picture on the right from the James Webb Space Telescope where you see distant galaxies, and you quite legitimately can say we can see them. Of course, the light then comes from far parts of the universe into a digital camera, and then we reconstruct images that we can actually see ourselves. Now, another example is a meteor, a shooting star. Perhaps many of you have seen a shooting star, a bright light zipping across the sky in a fraction of a second, and it ionizes the atmosphere and causes it to glow. And even though the shooting star itself, or meteor, is about the size of a grain of sand, and maybe 50 kilometers up, but we can still say we can see a shooting star. But the ionization had occurred. And this is how we actually can see particle tracks and visualize the particles themselves. So these are different ways of seeing, and I say that the eye happens to be part of that chain. So, and I just put here a beautiful picture of a retina, which is just, there's a beautiful picture. Art and science go together in so many ways. So here's a distance ladder. So I put this ladder, I got this picture from AI, of course. I asked for it to have about 40 rungs on the ladder, and every rung on this ladder is a factor of 10 in size, distance, a factor of 10 in size. So at the top of the ladder, the top rung is 10 to the 0 meters, which is 1 meter, which is about the size of a person, child, but you, who cares about factors of 2. And then a tiny grain of sand, the one you might have seen as a shooting star in the sky, is about 0.1 millimeters, a fraction of a millimeter, which is 10 to the minus 4 meters, written out 0.0001. There are 4, it's the fourth decimal place, that's why we call it 10 to the minus 4 meters. One should get used to these powers of 10 because they're so useful in physics, because we can't actually envisage these tiny distances without using a logarithmic scale. Some rungs further down the ladder is a protein molecule, which is, of course, many atoms together in a complicated molecule, which is perhaps 10 times bigger in linear dimensions than the hydrogen atom itself, which is about 10 to the minus 10 meters. And then 5 rungs further down, about 10 to the minus 15 meters, is an alpha particle, and about the size of protons, which are the nuclei of atoms. So you see there that they're five factors of 10 smaller than the atoms themselves. And so written out, it's 0.30000000001 meters. And I could see, when I was a kid, alpha particles in my dad's luminous watch, and I'll come on to that in the next slide. But in our experiments in physics, we've been able to detect particles that are inside protons that are much smaller, called quarks, and the electrons that go around the atom in their orbits. And these are much smaller than we can detect with our biggest microscopes, if you like. They are smaller than 10 to the minus 19 meters in length. And then, is that the smallest possible thing? Well, no. Things can be much smaller than that, even though we can't experimentally study them yet, and maybe we never will be able to. But way down, many orders of magnitude down, is what is the smallest possible length in the universe, which is called the Planck length. And it's 1.616 times 10 to the minus 35 meters. And it's formed out of three fundamental constants, which are the speed of light, Planck's constant, and the gravitational constant of Newton. I'll talk about that right at the end. But in this vast distance gap on a logarithmic scale between the smallest things that we can see even with our biggest microscopes, which is actually the Large Hadron Collider at CERN, there are many orders of magnitude, and we don't know what's down there from the physics point of view. Theorists have many ideas what might be. Maybe there's nothing really there until you get down to the Planck length, or space could be full of complicated stuff that becomes more and more complex until we actually get down to the Planck length itself, which is the ultimate simplicity, I would argue. So about a shooting star. I think many of you will have seen shooting stars, and you know they're meteors like a grain of sand. I asked AI to generate a picture of a girl looking at the shooting stars on a starlit night, and it came up very quickly with this rather nice picture of a girl admiring the night sky with the Milky Way and stars, and these shooting stars. There are two or three things wrong with this picture. One is that you don't usually see several at the same time. You see one, and then a few minutes later you might see another one. And they're also not parallel. They're parallel in space, but because of the perspective, they seem to come from a radiant in the sky, a particular point in the sky. But anyway, we're able to see these tiny grains of sand. Now, 70 years ago today, as I gave this talk, it was on the 9th of August, 1956. That was my astronomy notebook. I used to go out in the middle of the night and look for the Perseid meteors, which have a maximum around this week, middle of August. And I wrote down them and plotted their positions on the sky. And you see they are indeed all coming out from a particular point in the sky in the constellation of Perseus. Now, these grains of sand are traveling at about 180,000 kilometers an hour, which is, you can sort of calculate that in your head if you realize that they're 50 kilometers up and they go across in a second, and that means 180,000 kilometers an hour. So they're really fast, and their speed is heating up the atmosphere and making it glow. So I started as a teenage astronomy passion. Here I was out in the middle of the night looking for Perseid meteors. And then when I finished school, I did a bachelor's degree in physics and decided to go into particle physics because I realized I could always enjoy astronomy and be a professional particle physicist, but the other way around might not work so well. But in the end, I ended up doing some cosmic ray astronomy that I will mention towards the end of the talk. So coming back to particles now. So for over 2,000 years, we thought that atoms were perhaps the smallest pieces of matter, but they're not, because in 1897, which happened to be the year my father was born, J.J. Thomson at Cambridge was studying the conduction of electricity in gases. And you may know neon lights and argon lights, and gases will glow when an electric current is putting through them. So what J.J. Thomson did was evacuate the vessel, like a bottle, a glass bottle, if you like, pump it down to see what happened. And of course, eventually, the glow sort of disappeared as you got a better and better vacuum. But what continued was a glow at the end of the pipe, where he found that a beam of particles was going from the cathode, which is a negatively charged electrode at the bottom, and he made a beam of these particles. And what he did, which was original, was found that they could be bent, this beam could be bent by an electric field with a battery going across, and that would bend the beam in one particular direction. But then he found that if he applied a magnetic field at 90 degrees to that, he could cancel the bend and make it go straight. And by comparing the strength of the electric field and the magnetic field, he could work out the mass of these particles that were going through the so-called cathode rays, and conclude that they were indeed particles that have about 1/2000th of the mass of a hydrogen atom. So he discovered the first fundamental particle as an electron that's much smaller than atoms, and atoms are not, therefore, the smallest pieces of matter. And that is, I've seen the apparatus that he used at Cambridge University, in a museum there, like a bottle, that small apparatus there. So he actually is credited with discovering the electron by measuring its mass this way. And then some years later, Rutherford and Marsden at the University of Manchester, where I went to do my Ph.D., discovered alpha particles, which is actually helium nuclei. So they shot these alpha particles that came out of radioactive decays into gold foil, actually, and they expected them to be just going straight through, because at that time the idea about an atom was that it was a rather fuzzy thing, with electrons scattered around in it, but basically like a plum pudding, a sort of so-called plum pudding model. But he found that these alpha particles could be scattered sideways or even backwards, and therefore they had to get very, very close to most of the charge of the atom was in a small spot in the middle, which turned out to be the proton in the case of hydrogen. And so on the next slide here, I show my first time I saw particles, which was my dad's radium watch. He had a radium watch, which was one of the luminous ones that were radioactive, with radium in zinc sulfide, which is a phosphor that glowed when the alpha particles that came out of the helium nucleus actually excited the atoms in zinc sulfide and made it glow. And a picture on the right here is of one of those old luminous watches that were based on radioactivity. And I have lost that, unfortunately, that watch. It would still be radioactive because the half-life, or the time half of the radium atoms decay, is about 1,600 years. But it probably won't glow anymore because the zinc sulfide itself disintegrates after a while and doesn't work. But on the left, you see this picture of a tiny speck of radium on a photographic plate. And the scale you see is 0.1 millimeters, or a tenth of a millimeter, which compared with the fly's compound eye, which is 5-10 times bigger than that little bar. And the tracks that you see coming out are these alpha particles that are being ejected from the nucleus of the radium on the photographic plate. And they ionize the atoms along the path and leave tracks in the photographic plate. So this was a way of visualizing these atoms, these tiny alpha particles that are actually much smaller than the atoms themselves. So it showed that the alpha particles are 100,000 times smaller than the helium atom itself, which itself is about a millionth of a hair's width. So we're now starting to see things that are really, really small by the tracks that they make, in this case in photographic emulsions. So when I was a kid, I was lucky enough to be able to go up to some science lectures at the Royal Institution in London, and there was the lectures about seeing the very small, and that meant atoms in that time, not particles. But there's a picture that was in the back of the Times newspaper in December 1959, and you see there on the third from the left, looking at this little cloud chamber, which was a small device full of a vapor with a radium source in the bottom. And the radium is kicking out these alpha rays, which these helium nuclei, and making little soft fuzzy tracks in the cloud. That's called a cloud chamber there, a diffusion type of cloud chamber. So this was very exciting when it was found that you could actually see tracks made by these alpha particles in this device, a cloud chamber. And so, of course, C.T.R. Wilson developed this, and he got the Nobel Prize for that. He was studying clouds, actually. He went up to Ben Nevis to study clouds, and then he tried to make clouds in the laboratory in Cambridge and found that he could actually make clouds in his lab there. So that's a picture of tracks, fuzzy tracks of alpha particles going through this little diffusion cloud chamber. And that was part of my early interest in my first particle detector, where I could actually see tracks laid by particles. Of course, it wasn't my detector, but I looked at it. And see the girl in the background. I'm wondering if she was excluded from the nerdy kids in the front because she was a girl. I don't know about that. But so then the cloud chambers were used, these devices where you could actually have a supersaturated gas, and as you expand it, then droplets can form along the tracks of charged particles that ionize the atoms in their path. And you see a trail of droplets along these lines. And this one was from a cloud chamber that was taken up to the top of a mountain, actually. But Blackett, who built this, was at Manchester University, and he left there before I got there. But he put these cloud chambers in a big, powerful magnet, and that would bend the tracks through the magnetic field and you could measure their speed or momentum and their charge that way. So in this picture, you see actually, you may be able to see a V on the top, right to like 7 or 8 o'clock. You see a neutral particle coming in, going to 2 charged particles. That was a discovery of a new type of particle that was strange because it was produced strongly and decayed weakly. Before I go on to that, the cloud chamber was good, but it's not very dense, and so often you don't get many interactions in it. So the bubble chamber came along. Glaser invented the bubble chamber. He was actually at Cambridge, but studying, he was a meteorologist. He was studying clouds. He went up to Ben Nevis and studied cloud formation, and then he went back to his lab to try to make clouds in the lab, in a vessel which was vapor, and he expanded it. And eventually he discovered that he could make particle tracks in the bubble chamber. Now, if you have a glass of beer and you can see, or maybe fizz, or you can see trail of the bubbles coming up from an imperfection on the inside of the glass. It's a tiny imperfection, but it's enough to form bubbles, and they come up from that spot. So you can in this way see tiny imperfections on the glass by where the bubbles in your beer are coming up from. Yes, Bob has a question. Wait.
No, just what year was the bubble chamber?
Oh, that's a good question. It was in the 50s, I think. I'd have to check. But it, of course, enabled us to have a denser target for seeing particles and putting them in beams of particles. And the biggest one here was a big European bubble chamber at CERN, which is a huge thing of liquid hydrogen. So it's a liquid tank of hydrogen, and when I send a beam of particles through it, you suddenly expand it. It was super heated, so it's about to boil, but it doesn't quite boil until particles go through it, and they kick out electrons out of the atoms on their trail, and that leaves a trail of so-called ionization. And when you expand it, bubbles form along that trail, and you can take a photograph of the bubbles and trail of bubbles, and then recompress it, and the bubbles go away, and you're ready to do it again and again. So I never used bubble chambers myself in my experiments, but here's a photograph of bubble in Gargamel. That's another big bubble chamber at CERN, and I think it's science making art. You can see again here, particles are coming from the left, from the accelerator, and they go through the liquid, they ionize it along their paths, which means kicking electrons out of the atoms, and that's enough when you expand it to form a trail of bubbles, and you take a photograph. And in the old days, they were measuring thousands and millions of these photographs on a special measuring device. Now, what you see here, many things. You see, in the middle there, you see one of these V particles, a neutral coming in from the left, decaying to 2 charged particles. That's this K0 again. You see spirals, which are electrons, mostly, or other charged particles, and they bend because the whole thing's in a big magnet. And the magnetic field bends particles to the left or the right, depending on their charge. And as they go through the liquid, they lose energy and spiral in, because as they get lower energy, lower momentum, they tend to spiral in and eventually stop. And you see little tracks of electrons are being kicked out of the atoms of ionization spiraling in. And so there's so much information in these pictures. And in the 60s, many of these pictures, thousands of these pictures were taken and scanned usually by women who scanned them and measured the tracks. And that was a very labor-consuming thing. Here's just a few other pictures because I consider these beautiful art. Here's one of an electron coming in and spiraling in. And as you see, actually at the beginning especially, you see it's not a continuous track. It's a trail of points. And you may say, and I can discuss this with Bob, you thought particles were waves, and the particles, how can they be waves and particles at the same time? Well, an idea is that when it ionizes an electron, an atom, kicks an electron out, it's a particle. And then it progresses as a wave until it hits another atom, and then it becomes a particle again. So in between, in the gaps between, it's behaving as a wave, but when it ionizes an atom, it behaves as a particle. So this is mysterious wave-particle duality. But here's coming in this liquid hydrogen, and losing energy and spiraling in to the middle where it's going to stop. And here's another picture. Also, I just consider this, so as a physicist, I see this beautiful art. The tracks have been colored just for the artistic display. You see a particle comes in from the left, The little green curly thing is an electron that's been kicked out of an atom on its path, and then it turns into a shower of more particles being created out of the energy. Energy turns into new forms of matter, E is mc squared, and one neutral particle comes through and decays to two charged particles. Again, it's a neutral kaon decaying to two charged particles. So these are bubble chamber pictures. But then, I say they have so much detail, but they're very difficult to measure, take time consuming. So spark chambers were made. Now the spark chamber on the left, you see, is a stack of metal plates with gas in between, and when a particle goes through, in this case a cosmic ray track coming from above, you apply a very high voltage, like 10,000 volts, between the plates, and sparks occur exactly along the trails of the ionization. And then you take a photograph, and you see a track coming down here with the sparks it takes. And made lots of photographs that, again, were measured by, we call them scanning girls, measuring these things. So when I went to Manchester, my professor said, we could maybe automate this. It wasn't his initial idea, but he got me going to build a wire spark chamber. Instead of having metal plates, this is one I made in '65. It had an aluminum foil on one side, and the other side was not a plate, but a grid of wires. And when the spark happened on a wire, the current went down the wire to the bottom where I had a series of little lights, and you can see the lights flashing up when a particle went through. That was a prototype. So then I made a ferrite core memory with 1 bit per cubic millimeter. That's a very low density memory compared with nowadays. And we made big spark chambers, and here's one for my thesis experiment, 65 to 69. So that's me on the left, and our technician working on the spark gap generation. When particles came from the left, on the left you see this black magnet, actually, a big magnetic field, and that bent the paths of particles as they go through the magnet. And what I was studying there was, again, this neutral K0 particle, a strange particle, decaying to two pions. The pions went through the magnet and through the spark chambers and made sparks on the wires that we could read into our computer, where we didn't have to have photographs to analyze them. But the thing was, I could be in the hall when the experiment was running. The beam was not so intense that you couldn't be there. Probably nowadays you wouldn't be allowed. But then you could turn the lights off, and you could see trails of sparks going through these spark chambers. So that was really cool to stand there. And when the event happened, there was a bang as we applied 10,000 volts to the wires, and you saw trails of sparks going through there. So that was really a cool experience to see those trails of sparks. And coming back to bubble chamber, I said I'd never used a bubble chamber, but when I was at CERN, I'd walk past a Gargamel in a building, and I could hear a bang. And I went in and I asked the operators, can you see inside that thing? And said, well, yes, there's a little porthole. You can look inside there, and it's all dark. And suddenly, bang, and there's a blue flash, and I could see the trails of white bubbles there. So I could see with my own eyes in real time those trails of bubbles. And I don't think many bubble chamber physicists actually looked inside and saw them with their own eyes. So then things developed from that spark chamber. '69, that's when I finished my Ph.D. Now those spark chamber, wire spark chambers, did not become the real game changer, because at that time a man called George Sharpak at CERN invented another wire chamber that had a very low voltage and just made little tiny signals on the wires, and that you could run at very high rates. This you're limited to about 1 per second or so, but he could rate hundreds per second, so he got Nobel Prize for that. And then this developed into other wire chambers, and this is one that was an experiment I did later at CERN, this is half a cylinder there, full of wires, thousands of wires, and we measured the discharges on the wires as particles went through. The picture on the right is one of our so-called event displays, reconstructed by a computer. In this case, we collided two beams of alpha particles. Remember the alpha particles that I saw glowing from my dad's watch? They put alpha particles, beams, inside a storage ring, colliding two beams of alpha particles in opposite directions, and the beams go perpendicular to the page. This is a transverse view. When the alpha particles collide, many particles were created out of the energy, producing tracks of charged particles that were recorded by the electronics on this drift chamber. So there you see, we reconstruct tracks. And some of them are bent slightly because they have low momentum. The straight ones have high momentum because they're not bent so much in the field. So this was now a development of these wire chambers, now we measured actually the drift time it took from the ions to get to the wires, which made it a very precise thing. And this led up later to a big electronic track detector. This is a picture from proton-antiproton collision at CERN. They had this super proton synchrotron, and Rubia and Vandermeer had the idea of putting antiprotons in the opposite direction. So here's a picture from this electronic bubble chamber. The beams are going across from left to right, colliding in the middle. A proton collides with an antiproton in the middle and produces all these particle tracks that are recorded electronically. And this led to the discovery of the W and Z bosons, force-carrying particles. And so now it's just, is this not working properly? Is this better? Okay. Oh, you should have told me sooner. Should I start again? Okay, thank you. Okay, so now about these particles. So this is a chart of all the fundamental particles that we have discovered so far. We think there may be more we haven't discovered yet. But you see, okay, the 6 mauve ones at the end are called these quarks. They're constituents inside protons, neutrons, and nuclei. And there's one called up and one called down. They're just names. There's a reason for them. But protons and neutrons are made of up and down quarks. The proton has 2 ups and 1 down, the neutron 2 downs and 1 up, and then the electrons going around the atoms. So all atoms are made of up and down an electron, the quarks stuck together, electrons going around. And then the electron has a neutral partner called the electron neutrino that interacts so weakly they come from the center of the sun, and trillions are coming through your little finger every second because it interacts so weakly, and but we are doing experiments with them now, especially at Fermilab. Then it was discovered, so that you see there on the right, the S, the strange quark, that was responsible for these K0s decays, and it had a partner called the charm quark that I was looking for, but others found it first. And then it has a heavier partner called a heavier partner to the electron called the muon, and its own neutrino. And the 5th and 6th quarks are top and bottom that were discovered at Fermilab, and I helped find the top quark in 1995 at Fermilab, and I'll show you a picture about that. And then in the red there you have the force carriers, the W and Z bosons that carry the weak force. They were discovered at CERN in that experiment I showed you just before. The photon is the particle of light, the gluon sticks quarks together in protons. And then the Higgs boson was the last fundamental particle here that we discovered at CERN in 2012, and I was privileged to be part of that discovery as well. So these are all the ones we know, and but we know that this makes up in about 5% of the stuff in the universe. There's dark matter, which astronomers and cosmologists tell us are there, and maybe dark energy particles too. So that's that, and I had searched through my career for charm particles. Others found them first. I had ideas looking for W and Z bosons. They were found by the other experiment, but here the top and the Higgs were being part of that, which was great fun and privilege. So the top quark was found at Fermilab, where I came over in 91 to work there, and I'm still working there. I retired 10 years ago, but here's an aerial view. You see that ring, it's 4 miles around. That's, of course, the road above the ring. It's a tunnel underground, sending protons and antiprotons in opposite directions, and they collide at very high energies to turn energy, of kinetic energy, into forms of mass. Bottom left here you see a 17-story building called the high-rise building. That's where my office is. I've still got an office there, and so on. And so this is west of Chicago, and that's where we found, well, this is one of the 2 big detectors there. I came here to work on that, called the Collider detector at Fermilab CDF, and we co-discovered this top quark with the other big experiment. And there you see it in an open situation where you see a metal box that's going inside. That just holds a cylinder that goes inside to do tracks with very precise little silicon pixel trackers. And then on the bottom left, you see that is a plug that's going to close that up, and the beams go through the middle and so on. So you see the size of these detectors getting bigger and bigger, and they keep getting bigger and bigger. So the top quark, well, this is actually a picture of the wire chamber that we had with tracks. It's much messier than the one I showed you before, but you have the information of the tracks in the other dimension as well. It's just a reconstruction here of how we see the tracks, and we reconstruct the origin of the tracks from by measuring their momentum and putting them all together. And this was actually one of the events that find the top quark. And here's a diagram that I made of how you have here protons and antiprotons colliding from the left and right. I say proton, it doesn't matter. And they're made of 3 quarks plus these gluons that bind the quarks together. And question, was that? No, gluon, oh sorry, a gluon. So just as a photon is a particle of light, or the electromagnetic field, the gluon is a particle of the strong force that sticks quarks together inside the proton. So the proton, as it comes along, it's got quarks, it's got some antiquarks and gluons, and 2 gluons, these quanta, they're confined forever inside protons. They never get out, but 2 can collide, and the energy of the 2 gluons turns into mass in the form of a top, in this case top, and an antitop quark. All the quarks have an antiparticle, which has the same electric charge, so it's opposite sign, but the same value, the same mass, and so on. So we found events where the gluons were colliding and producing a top quark and an antitop quark. This diagram just represents how the top quark going up to the top emits a W boson and becomes a bottom quark, and then emits another one and becomes a charm quark, another one becomes a strange quark. It's a whole cascade of decays. And meanwhile, the antitop does the same cascade, and I just put them in this diagram here. The W's themselves are unstable, and they decay in many ways, as in the diagram there. Now, I show that because you see here on the right a piece of art by my artist friend Shanti Chandrasekhar, and she based her art on this diagram. You can see in the middle there, there's 2 gluons colliding, and then all these lines are so-called Feynman diagrams of quarks and antiquarks and gluons coming out. So that piece of art is actually at the National Academy of Science. It's been there in an exhibition that I had with her, and they've actually bought this piece for their collection together with my writing that goes beside it. So this is just a segue to this exhibition with Shanti Chandrasekhar. She does amazing art inspired by science, by space, time, black holes, Big Bang, and so on, entropy, symmetry. And so that exhibition's been there for a few months, but it's now moving to the Keck Center in DC until December. So she does this art, and I write science or science poems that go with it. And in this book, actually, we have a little catalogue from a previous exhibition there, symmetries, singularities, and infinities, with her art and my science writing in there. But I show this other picture because last year, Kip Thorne, who got a Nobel Prize for discovering black holes colliding and emitting gravitational waves, was there, and he had an art and science exhibition there. And I went there with Paul Grundy, who is here. There's Paul, who's a member of the National Academy of Science for Medicine. And he went there, and he saw that lady sitting by herself and went and talked to her. And I joined them. It turned out she said she was Caroline Winstein. I said, oh, Winstein, I knew Winstein. I worked with him. It turned out his brother. But anyway, we had a nice chat. And then along came her husband, who happened to be Kip Thorne, and sat down with her. So Paul took that picture of me with Kip Thorne and Caroline Winstein. And she's actually got a copy of this little book in front of her, so that's a fun thing. So now let's move on to CERN. I don't know how I'm doing for time, but okay. So CERN is now the world's largest particle collider. It's 16 miles around, which is 27 kilometers. It's underground. If you've been to Geneva, you might recognize this Lake Geneva, and there's Geneva's over there in the background. There's the Alps block. I've gone dead. It's okay? That better? Okay. So protons go around in both directions here. There's some beams of protons around. They go around 30,000 times a second because they're going at 0.999999 the speed of light. They can't quite get up to the speed of light because that would require an infinite amount of energy according to Einstein's theory of relativity. You get more energy, you get more nines to the speed. You can't quite get there. And then they collide the proton beams. They focus them down to the width of a human hair, okay, 20, 30, 40 microns, at 4 places around the ring. And the one project I work on is called CMS, Compact Muon Spectrometer, over on the left. It's quite a drive over from the main site, which is over to the right there, through the country, so it's a huge thing. And now CERN is planning to build one even bigger that goes under the mountains, the Jura, the Salève Mountain in the background. But this is inside that ring. Okay, so it's 27 kilometers of superconducting magnets at 2 degrees above absolute zero with liquid helium in there. And there's a picture of part of this. So the magnets are 2 beams inside those magnets going in opposite directions. And that's a picture of me in the tunnel there, where I added some detectors along the beam to detect protons coming out at small angles. So, and there are two huge experiments there. There are four big experiments, but here's the biggest one called ATLAS, a toroidal LHC apparatus. And I just put this picture up there. It's a diagram of the thing. Look at the tiny picture. They have tiny people in ATLAS. My experiment, we have bigger people relative to the experiment. But you can never see the whole thing all at once. And you can go down in the tunnel, where you go down to see it when it's not operating, and it's just so incredibly impressive, but you can only see a tiny part at the same time. It's in a huge underground cavern. And this is a picture of it. Also, you see these radiating things there, magnet coils, superconducting magnet coils, that make a toroidal magnetic field that goes around the beam, and the beam will be going through the center of that thing, and there's somebody down there. You can see the scale of this thing. It's just huge. And this is the experiment I'm working on called compact muon solenoid, about 2,500 other physicists on this. So some statistics down there. You can see it's opened up now, but when we start to run, it closes itself up. The man gets out of the way before he gets crushed, of course. And there's 12,500 tons of iron. There are 80,000 crystals of lead tungstate, which is a very heavy, dense material, 98% metal by weight, and yet it's transparent. So when particles go in there, they make flashes of light, and that can be recorded by photodetectors. And this is actually quite obsolete now, but we have more electronic channels now, but writing 10,000 encyclopedia channels every second when we're running, and the information is condensed and sent out to the States and around the world. It's not just a picture of it. It's like a huge digital camera to see tracks of particles that come out of the collisions. And here's one of these events. Now, I've given a talk about this before, the Higgs boson, which is showing that a field filling the universe, called the Higgs field, if you like, actually gives particles their mass. And I gave a Science Sunday talk here in January about it. Now, how do we see this? We don't see it as tracks because it decays so close to the protons that collided that you can't see tracks. But you can see, in this case, it decayed to two high-energy gamma rays, which are photons, and they're marked as green lines there. So you reconstruct these events, you reconstruct the energy of the photons and the other particles, and you make a plot of the mass of the two photons. And here is one of the discovery paper plots. On the right, you see the mass of two photons, saying, if these two photons came from a particle, what would be the mass of that particle? And you see it's a smooth line with a bump on it. So that bump is showing the Higgs boson, not as a track or anything, but as a bump in a plot. And on the left, I show a talk from that I worked with on this idea with Jim Verdi in 1989, and we talked about whether we could see the Higgs decaying to gamma-gamma if we had a really challenging detector with really good energy resolution. And we didn't know the mass of the Higgs. The plots on the left show if it was 100, top of 100 GeV, you wouldn't be able to see it there. 150 GeV, it's very challenging, but we did actually see it that way 23 years later. I'm sorry we didn't publish that paper because I was too busy doing other things. But anyway, that's one that got away. But I was there part of the discovery, 2,500 others. Now here's another picture. This is actually me back in the Tevatron, installing detectors along the beamline in the tunnel to detect protons that have been scattered out of the collision and producing some particles in the middle. You see I've got a yellow backpack on there. That's because in case there's a leak in the tunnel, you have to be able to put the backpack on and get out quickly. Of course, you're not allowed to be in the tunnel when it's operating. But on the right, you see one of these pictures of an event that happened at the Large Hadron Collider in the early days when we still had protons colliding singly, and in this case, it produced two sprays or jets of particles coming out sideways, and you see the tracks reconstructed. The protons are colliding along that diagonal line there. They collide in the middle. They lose a bit of energy in creating those two so-called jets of particles, and then we detect the protons along the beamline. Now, those jets are caused by quarks or gluons inside the protons scattering sideways. Now, the force between them is incredible. It's a strong force. Now, you can imagine that Large Hadron Collider, as I say, it's 16 miles around, so it takes 4 miles to go through 90 degrees. To bend the particles with very strong magnets through 90 degrees takes 4 miles. But here they're being kicked out sideways in 10 to the minus 13 centimeters. So the force is incredibly strong, kicking those things out. Now, by measuring the rate at which those things are kicked out, we can infer that the quarks inside the protons are smaller than 1/4000th the size of protons. So we're now getting down towards the infinitesimal, down the ladder. We're now seeing the quarks are less than 1/4000th the size of protons. And that's as far as we've really got now, but we get higher energy as collisions. When the LHC started, some people were worried that we might cause a black hole and swallow the Earth, by the concentration of energy. But actually, there are high energy particles coming from the sky, hitting the Earth, and they haven't made a black hole yet to swallow us all up. So we said that's not going to happen. But now we study these high energy particles that can have particles thousands of times higher energy than those in the Large Hadron Collider. And they come from outer space, from we don't know where. Somehow they're extremely violent events in the cosmos. But we started building detectors to see these showers. But when the particles hit the top of the atmosphere, the energy of the collision with a proton or nucleus in the atmosphere, nitrogen or oxygen, makes many, many more particles, and they make more and more in a cascade. So by the time they get down to the ground, they can be spread over many square kilometers. And so how do you build a detector for them? Well, you sample the shower, and I think the next slide, okay. So Jim Cronin, who got the Nobel Prize before for showing that matter and antimatter are not identical, there's a violation of the symmetry between matter and antimatter, and he started this project. I met him at Fermilab, and he asked me if I'd help with the design report. We went down there to the site in Argentina. They chose a site where the skies can be very dark at night on moonless lights, so you can see the flashes of light in the atmosphere that one particle can make. We saw them making flashes of light before, but here they hit the atmosphere and they can make a flash of light. And that's a picture I took of Jim Cronin, who started this project. And it's like the Aurora Borealis. How many of you have seen the Aurora Borealis? It's a beautiful sight, right? You don't see it from here very easily, but I saw it best from northern Lapland, and great, amazing thing. You see the lights in the sky moving around, and the ionized oxygen and nitrogen in the atmosphere. And these are trillions and trillions of particles coming from the sun, the solar wind, and they hit the atmosphere and they make the whole atmosphere glow. Now, it's the same basic principle that we can see these cosmic rays, individual ones, have got such huge energy that one particle can make enough light to see on a dark night if you've got really good eyes as big as dinner plates. And so it's the same principle. So we made eyes as big as dinner plates. So here's this observatory in Argentina. I was down there at the beginning of that, and we had 4 of these little observatories with a telescope inside. It's like the fly's eye I showed you before. You can see here on the right a whole bank of photomultiplier detectors, and the image of the night sky is put on those things, and you can actually see on dark nights this trail, a shower of particles made by this ultra-high energy cosmic rays. They're so rare at the top end of the spectrum that there's 1 per square kilometer per century there. So how do you see them? You make a detector that's many square kilometers, and then you wait and you see them. And here's a sketch of the water tank. So here we made 1,300. They made, after I started this thing, it was part of the beginning. Those water tanks are like backyard swimming pools, and they have photomultiplier detectors inside to see flashes of light that charged particles make in the water as they come through. Any question? Yeah. So, yeah, it's very cool. So those are just stacked up there, waiting to be put in the desert, a kilometer apart. So the 1,300 of them are a kilometer apart. They cover 3 times the area of the city of Chicago. And then when a cosmic ray shower comes in, it can hit dozens of these at the same time, almost the same time, and you see these flashes of light. So when you see many tanks with a flash of light, almost the same time, you say a cosmic ray shower came in, and by timing very precisely the flashes, you can tell the direction it came from, because it comes in like a sort of dinner plate coming in, and the ones that hit first give an early signal and then the later signals. So you can reconstruct the position in the sky it came from. And this is a sky map of these ultra-high energy cosmic rays, and you see a hot spot there that's probably from a very active galaxy, but the resolution is not so fantastic like in optical astronomy because these cosmic rays have electric charge and they get bent by magnetic fields in the galaxy, so they tend to get spread out unless you go for the really, really highest energy ones. So that's cosmic ray astronomy now that I was lucky to be part of in the beginning. I had to leave it because I did two other projects at the same time. And then here's the other amazing new form of astronomy, neutrino astronomy. We see neutrinos coming from the sky, and they come from the sun. And I'm going to talk about these astronomies. But this is an amazing project started by a friend of mine called Francis Halsey, and he instruments a cubic kilometer of the ice underneath the South Pole in Antarctica. As 1 billion tons of ice. So how can you do that? These particles, if they interact, I mean, they interact so weakly, but there's so many of them, some can interact and make a shower of particles that make flashes of light in the ice. So we want to detect the flashes of light in the ice deep down under the surface in Antarctica by the South Pole. So the clever way of doing that is to drill holes with hot water. So you have hot water and you put a hose down in the ice and you can melt like this sort of size of a pillow of ice down all the way down, and it stays ice. It stays water for a week or so, and while it's water, you can drop down a string of photomultiplier detectors that detect flashes of light, and then it all freezes over. So they're down there, and they'll be down there until the Antarctic ice sort of flows down and strips away the caves. But then they have seen neutrinos coming from the sky, and they can plot where they come from the sky. Neutrinos having no charge, they go straight, unlike cosmic rays, so you can really plot where they came from in the sky. And this is on the right. Here you see a plot of, well, above there you see like signals and flashes of light in the tubes. There's a galaxy called NGC 1028, 1068, emit 77, a spot in the sky of neutrinos coming from there. We've seen them coming from the sun, from supernova, and so on. So we're using neutrinos now with super high energies to do astronomy. So I'm coming towards the end, but here's this ladder. It's called, you know about the Ouroboros, a snake biting its tail, right? It's an old religious symbol. And Glashow, who got a Nobel Prize, he made this diagram of the scales. So at the bottom you see 1 meter. That's typically us, a kid or so. And then all the tick marks around to the left are smaller and smaller. You have biology, you have the proteins, chemistry, atomic physics, nuclear physics, particle physics. That's how far we've got. And then you have a whole unknown region of scales down to what's called the Planck scale at the top. And I'll tell you what that is again in a minute. And the other way, going bigger and bigger, you have the Earth, you have Earth sciences, you have the solar system, you have stars, you have galaxies, and to the cosmology, the whole universe. And now we believe that the whole universe started at the Planck scale, started much, much smaller than a proton, the whole thing, and blew up, basically, towards the Big Bang. So it's closing the circle, if you like. When we study particles, the very smallest particles, astronomers on the other side are reconstructing the beginning of the universe and finding that at the very beginning of the universe, it was so hot and energetic that all these particles were created, top quarks, everything were created. So that is the ladder, if you like, that I showed at the beginning, but wrapped around in that cosmic Ouroboros, which is an old religious symbol. Now this is a technical slide, but I put it in for completion. So at the bottom of the ladder, we have what we call the Planck scale. Perhaps that is the absolute bottom, I think so. I don't believe there could be a point of zero size and infinite density. There are three fundamentals in science. C, which is the speed of light, that relates space and time. You see at the bottom there, space-time. Actually, call this a STEM diagram. STEM, space-time, energy, momentum. Space and time are related by the speed of light, the expeditivity, the speed of light. And also momentum and energy for a photon is related by the speed of light too. And then on the right you see energy and time that are related by Planck's constant, h or h bar. And the momentum and space are related also by h bar. That's the so-called uncertainty principle. And in the middle is g. G is Newton's gravitational constant that relates space-time and energy momentum. It's how matter bends space and time. So from those three constants, this is you see here, the whole story about how symmetry in space leads to conservation of momentum, symmetry in time to conservation of energy. These are Noether's theorem, and Emmy Noether was a mathematician who developed this, proved that if things don't change in space, momentum must be conserved and so on. Very brilliant thing. And energy momentum bends the shape of space-time. That's Einstein's general relativity. But when you put those three constants together, you can measure them in the laboratory at speed of light and so on, and you measure them very precisely, and you can put them together to make a length called the Planck length, and it's 1.61625. 18 is the uncertainty in the last digits, 10 to the minus 35 meters. So that is perhaps the very smallest piece of space you can have. The Planck time, which is 5 10 to the minus 44 seconds, is the time it takes light to go that length. And you can also put them together to make a mass, which is surprisingly about 21 micrograms, which is a physical space. That doesn't mean that you can make an ant and make a black hole out of it, but if you had that much mass in that tiny piece of space and time, then that would curl space so much according to relativity that space becomes frothy or something. That's called, it's a quantum theory of gravity. We haven't got quite there yet. It's not worked out yet. But I believe that this is at the bottom end of the ladder, the smallest you can go, the end of space and time. Now, so I had to put a cartoon here. Einstein discovers that time is actually money. Gary Larson has such great cartoons, right? Okay. And so now is a commercial break, the first one, which is in my book that came out last year, which I have a copy of it here, 100 short stories about the universe. And it's been on Amazon for a while, and you can pick up cards with QR code. So that is, and I was at a conference in California, and World Scientific Publishing saw that and asked if I was doing another book, and I sort of said, well, I am now, and this one is to be published anytime soon, called Seeing Particles, Adventures of an Experimental Physicist. So it's memories of my 62 years now studying particles, and it's got a lot of personal stories in there, and so that I have here. If you want to pick up a little wallet card, the QR code, it should be available for purchase anytime in a couple of weeks. These are just an advanced copy that I managed to get them to send me in time for a conference at Fermilab 2 weeks ago, where there's about 500 particle physicists, so they got to see the book. And there's a flyer here. So I think there's 6 minutes for questions and discussion. Thank you. Paul.
Have they ever found an antineutrino?
That is the question of the day, neutrinos, antineutrinos. So yes, we have found antineutrinos and neutrinos. Neutrinos are very strange particles because it depends on how you look at them. When they interact, when they're created or destroyed, they are either electron type or muon type or the tau type. There are 3 different types. But they mix with, in the propagating between the sun and the earth, for example, they come as waves, and there are 3 different mass states. So there are 3 mass states and they all have antineutrinos as well. But the big question is a neutrino and antineutrino the same thing? So neutrinos, because we now know they have some mass, a very tiny mass, but in principle you could catch up with a neutrino and you can even overtake it, and it looks like it's going backwards. And does it stay as a neutrino going backwards, or does it turn into an antineutrino? These are big questions, and Fermilab have a big program to study these things. So yeah, neutrinos have antineutrinos too, and they have, so yeah. So even though they don't have electric charge, they're different in other ways. They have a different weak charge. So, but people are looking to see whether there's a thing called neutrinoless double beta decay. When an atom decays to spitting out electrons, usually an electron and a neutrino, can it decay 2 neutrinos? Looking for that, and a big experiment looking for that, very rare process, but that would prove whether neutrinos are their own antiparticles or not. Okay. Yeah. Wait, please. I say wait because it's on YouTube, so the questions should be there.
I was just curious, how much do these colliders cost, and who's funding them? And is funding still available?
Well, okay. So, yeah, they're not cheap. So Fermilab, I can answer Fermilab first. Fermilab costs the US taxpayer, like you, about $1 a year per person, okay, which sounds quite a lot, but it's... and now CERN CERN is much more expensive. I mean, that collider has cost perhaps, don't quote me, but 4 or 5 billion, which is paid over like 10 years by all the countries of Europe. They're members of it. There are 60 members of CERN. Well, all the European countries are members of CERN, and they all pay according to their national gross domestic project. And then the US is a visitor. We work there. There's 1,000 US physicists working at CERN. So yes, they're big projects. And they are expensive, but they are. There's so much. Well, they have so many practical applications in a sense. I mean, much fallout because we push the boundaries of technology. Like the World Wide Web. Use the World Wide Web. Where did that come from? It was invented at CERN to enable us physicists to communicate through different platforms together. Medical imaging, MRI scans, use magnets, superconducting magnets, developed by Fermilab to make that accelerator. So there's not a justification for us to do it. We want to understand the universe, matter, space, time, right? It's like, astronomers wanted to understand what stars are. Now we do understand them pretty well. So, and CERN now wants to, planning to build a much bigger collider to reach higher energies and look for dark matter particles and so on. But it's not as expensive in money terms, but on the overall scale of things, it's a small contribution. Right? It comes from the Department of Energy. So far, not been defunded, but National Academy of Science is sort of being defunded. So it's an if thing. However, one talk I give is about science for particles for peace. Because by CERN, you have countries from all over the world, including Russians, Chinese, Americans, all collaborating together because science is universal. And there's a great force for peace in the world, the fact that we can collaborate. And I had worked with Russians and Chinese and Americans on the same experiment years back. So from that point of view, it's very valuable, I think, for bringing peace about. So helping anyway, till Russia invaded Ukraine, and that was a fly in the ointment, if you like. That was an annoying thing. More than that. Other questions? I pass the microphone. Yes.
And this is quite probably off topic. I notice all the spirals flow counterclockwise. When they're going, is that consistent?
So when a particle goes, the particle's traveling along. And if you put a magnet there, the magnetic field bends the particles to the left or the right, depending if it's electric or negative or positive charge. And the lower the energy it has, the more it spirals up, right? So obviously a car going around a bend, if it's got very high momentum, it tends to go straight. It's got low momentum, it will bend. When a particle goes into a liquid, like those bubble chamber pictures, as it goes along, it kicks electrons out of the atoms, called ionization, and loses energy. And as it loses energy, it bends more and more, and then bends more and more, and then spirals into the middle, and then stops. Okay. Does that answer your question? Sorry? Well, some go the other way, because the electron has an antimatter particle called the positron. And that spirals the other way because it's got a positive charge. It's just like an electron, but it's got a positive charge. And you can make an electron and a positron together out of just gamma rays. I've done that experiment. But the positron, if you ever have a PET scan, the P stands for positron. And it's a practical application of antimatter, in a sense, because the positrons are emitted by a radioactive isotope that's injected to you, and the positron annihilates with an electron, and so you make gamma rays that come out sideways, and you detect the gamma rays, and then you can see where that happened. And if it happened in a part of your brain that's very active, then you can figure it out. So I say PET scanning is an application of a positron. Now, don't talk about antimatter bombs, because they don't work, okay? But, actually, yeah. You have to wait the microphone because it's recorded.
You just touched on that because the PET scan, what I was thinking is, how does this relate to an MRI?
Okay. Well, medical imaging is a big fallout. MRI doesn't use positrons, it uses magnetic resonance imaging, and you need to be in a strong magnet for that. And the strong magnets for MRI, there was a push by Fermilab. We want to build really strong superconducting magnets to make a 4-mile ring with these. So we had to push industry to do that, cheaper and better, and that was sort of stimulating them to develop superconducting magnets that then have taken part in MRI scanning. And so another application actually, so neutron therapy was something, that's another application of particles like neutrons for cancer therapy, that was actually invented by Bob Wilson, who was a director of Fermilab before I got there. He'd been part of the Manhattan Project, but afterwards he said, we could use neutrons to help cure cancer, maybe radiate cancer, because when they go into the body, they don't ionize because they're neutral, but as a slow down and stop, then they can make a big ionization. So you can actually tune the beam to irradiate a deep part of the body. So now there are over 30 neutron therapy centers in the country for cancer, going along with gamma ray therapy and so on. And then light ion therapy is being done as well, carbon beams and so on. So these are applications, but not to do with PET scanning or positrons.
So, magnetic resonance. We used to call it nuclear magnetic resonance, and they changed the name of it because nuclear sounded scary. But literally, it's taking a huge magnet, and it's going against the proton, and it forces them all to align to a certain magnetic field. And when you release that magnetic field, and they go back to their random phase, they let off a photon, and some neutrons too, I think. But it's those photons that are captured by an image, and then that makes the image that we see of basic human anatomy. When I started medical school, it was like looking at imaging was like, I mean, you looked at an ultrasound and it was like this grayish field. It's now an anatomy textbook we're looking at. It's really, really amazing. So, yeah, cool.
So while we're on the subject of applications, I remember the story. So I showed you a picture of me looking at that cloud chamber at the Royal Institution when I was a kid, right? In that lab was Michael Faraday in the 19th century. And Michael Faraday, so he was an apprentice bookbinder, and he read the books that he'd bind. And then he became experimenter at the Royal Institution, and he invented the electric motor and the electric dynamo. I mean, imagine he was able to show that electric current flowing through a rod in mercury would turn around. He was turning electricity into motion, so that was the beginning of electric motor. And then later he did it the other way around and made a dynamo where a moving magnet could create electricity. And so that was just pure research, and it led to motors, dynamos. And Margaret Thatcher famously said that his work in the Royal Institution was worth value all the stock exchange in the country, everything. And then, these things lead in surprising places when you start out just trying to understand the universe. And then, so Faraday did that, and then at the same time, a Scottish physicist called Maxwell, he was playing with the equations of electricity and magnetism and things you could measure in the lab, and then he found that when you put these constants together, you could put them together to make a speed. And the speed it comes out is about 300,000 kilometers a second. The speed of light comes out. So from lab experiments, he derived that, speed of light comes out and electromagnetism and all the rest follows.
I was struck by the amount of data that this thing collects. And I'm making a guess that a lot of the experiments you design ahead of time, you're guessing what you're looking for, and therefore you set it up. You stack the deck to answer the question you ask. Is anyone exploring those data sets to find anomalous things that don't fit the model so that you might actually find new physics? I mean, I keep people busy for a while.
Yeah, no, I agree, absolutely, because when the Large Hadron Collider is operating, every 25 nanoseconds you have like 25 collisions. That's billions per second, and you can't record them all, so we have electronics that says, we're interested in ones producing an energetic electron or muon or whatever, so we've set up a filter and filter out the ones we think are most interesting. Now, the others maybe are containing some very interesting things. So we do have programs to look at the other events, so you can't look at all of them, but try to look for anomalies. So we have anomaly detection programs that people write, to look for things that are unsurprising. Like with the sky, you can do you can see pictures from the James Webb, and public can look at them and see if they see anomalous things that don't look like normal galaxies or whatever. So that's Yeah, so you're right. I mean, there could be all sorts of interesting things hiding that we haven't looked for because we weren't looking under the right lamppost or whatever. Any more questions? Yes, Judy.
This is great presentation, fascinating subject, and but one of the things that I was really struck by is where you had a picture of your report that you wrote when you were 12, 13, that you were looking at the sky. Did you envision particles at that point? Were you envisioning what you eventually came to work on?
Well, it's hard to remember, but I mean, I do remember being fascinated by seeing these little sparkles on my dad's watch when I was under the bedclothes in the dark with a magnifying glass, But did I ever think, what I'm seeing is, a trillion times smaller atom? I don't think so. I'm just fascinated by that. So it evolved, yeah. Yeah. Well,
Let me cheat and ask another question, and that is, as physics progresses, we are answering many of the questions we came to it that motivated us to look, but we're also generating a lot of new questions. Has anyone done a catalog to say whether we're winning or losing that game? Seems to me we're generating more questions than we are answers.
Right, well, as the boundaries of knowledge expand, the boundaries of ignorance expand, right? So, we found, go back when my dad was born, okay, people thought this was the earth and heaven, right? That was it, the earth and heaven, and the stars in the sky. And then we figured out, okay, there's a Milky Way galaxy, and then but whatever. So, of course, we have lists of questions, and one thing that is really fascinating us now is because the stuff we're made of, atoms, planets, galaxies, everything, it's only about 5% of the stuff in the universe. And cosmologists say there must be more stuff there that has gravity. For example, Vera Rubin, a women astronomer, who saw that galaxy rotation curves mean there's more mass there than we know about. And we think it's made of particles we haven't found yet. That's one question, but there's so many questions we have. What gives rise to the mass of the particles? Why do they have the masses they do have? I have given a talk here about miracles of physics that allow us to be here, So how come the neutron's a bit heavier than the proton and decays to it? It's the wrong way round. The proton should be heavier than the neutron. But if it was that way round, we wouldn't be here, right? So there's so many questions, and I don't think, Stephen Hawking actually thought some time ago that we're going to get to the end of theoretical physics. We'd get to the end of it. He was just wrong about that, It's just wrong. People have been wrong so often, right? And long may it continue, actually, long may it continue. But we learn more wonders. Anyway, thank you for coming, and yeah. And if you want to look at one of my books, I've got some up here. So.